let's move on to actually building the model. And it's really easy. We just use the ln command. So remember the ln command for bivariate regression was ln bracket and then the dependent variable and then a squiggly, which is called a tilde, and then the independent variable. Same idea. We have ln, the dependent variable, a tilde, and then the first independent variable, filter length, and then plus the next independent variable, build length, plus build depth. So we just sequence them one after the other with a plus, which kind of mimics the equation. Yeah?
Does order matter when we're adding?
Yeah, so the question is, does the order in which we add these independent variables in matter? No, not for this. Once we get into more complicated ANOVA style models, then under certain circumstances the order could matter. But for our purposes, no. Okay, so the ln command, just like before, and then we save the results of that into a variable I'm calling mod.full. I'm calling it a full model because it contains all the independent variables that we think might be important for our predictive model. 3 of them, yeah.
Could we apply matched pairs design to this?
Could we apply a matched pairs design to this? Tell me more.
Like if we were doing an experiment where instead of having just like data points, we were looking at matched pairs maybe from like participants in one condition versus how they respond in another condition.
Oh, I see. If we had data for participants in one condition versus another condition. Yeah, in that situation, the condition would be you could make that condition another variable, and it would be not a continuous variable like weight, it would be a discrete variable, a categorical variable. And the real answer to that question is once you start doing that, you're basically doing analysis of variance. Yeah. So we'll talk about that later in the course. Yeah, right now, just a reminder, all these variables are continuous variables. But in principle, you can have a variable in a model that's not continuous, that's categorical, like placebo versus drug. And when you do that, as we'll see later in the course, you're doing a form of analysis of variance. Okay, the model object, if you apply summary to the model, just like for bivariate regressions, it gives you a lot of stuff. It reminds you what the function call was. It gives you some information about the residuals. And it gives you here, under coefficients, the actual coefficients of the model. The intercept, just like in bivariate regression, is the value of the dependent variable when all the x variables are 0. So, according to this model, the penguin's weight, when the flipper length is 0 and the bill length is 0 and the bill depth is 0, and the penguin doesn't exist, then it weighs minus 4,341 grams. Clearly, that's not very useful to us, right? And there's multiple reasons why that might have emerged. Probably if you actually track these variables, in penguins right from birth or something, when they were teeny tiny penguins, you would have some kind of exponential relationship, not a linear relationship. So we're dealing out here with adults, and so if you sort of shoot a straight line down to 0, you're probably going under where the actual curve would be. So in general, the intercept term of the multiple regression is not terribly relevant or interesting to us. It's the value of the dependent variable when all the independent variables are 0. I mean, there might be a situation where it is interesting to you, but a lot of the time it's not. The real things of interest are these 3 slopes here. Flipper length, 17.421, build depth, 55, build length is 55, build depth is 141, let's say. Those are the beta 1, beta 2, and beta 3 variables in the model. Those are the slopes. That 17.421 means, according to the model, when flipper length changes by 1 millimeter, when flipper length increases by 1 millimeter, the penguin's body mass increases by 17.421 grams. So these slopes are in units of the dependent measure, in this case grams. This 55.368 slope on bill length means that, according to the model, when bill length increases by 1 millimeter, which is the units are in millimeters, body mass increases by 55.368 grams. And bill depth, same idea. When the bill depth, which is the sort of vertical thickness of the penguin, increases by 1 millimeter, then the penguin's mass increases by 140.895 grams. Okay? Yeah?
Is that intercept just an average of the intercepts of all the individual relationships?
Yeah, that's an interesting question. The question was, is that one intercept, is it some kind of average of 3 intercepts, one for each of the 3 relationships? I don't know, to be honest, if that's mathematically true or not. I've never thought about it in that term, in that way. I guess in the way that we sort of took different views of that 3D plot and we had a slope, you could also identify an intercept for each view. And then, would this be the average of those? I don't know, is the real answer. I'm not sure.
I'd expect them to have different intercepts, each of them, slightly. If they have different slopes.
Yeah, that's true. If they have different slopes, then they ought to have different, they ought to intercept the y-axis at different points. Yeah, I don't know. It's a good question. I'll leave it as an exercise for you. Yeah, I'm not sure. The way I always think of this intercept is it's the one place that the plane, or the hyperplane, if it's in more than 3 dimensions, it's the one place where that hyperplane intercepts the z-axis when everything else is 0. Okay, so really it's those 3 slopes that are the most interesting thing that comes out of this model, because that tells you how the dependent measure varies with these 3 independent measures. You get a t-test and a p-value for each of these 4 things, for the intercept and the 3 slopes. The test on the intercept, it's not so useful unless you have a situation where you really actually are interested in the intercept. It's these tests on the slopes that are relevant. And in this case, the p-value for each of these 3 slopes is teeny tiny, 0.0001, 0.0000000181, and then 8 zeros and then 3 5. So they're very tiny p-values, which means that the probability that you could have ended up with a slope estimate this big in a sample, if the real slope out there was 0, the chance of that happening is really tiny. So you interpret that tiny probability and you say, well, I'm not that unlucky. I think the slope out there isn't 0. Because if it was, then this is the chance I could have observed an estimated slope that big if the real slope were 0. That's a tiny probability. I'm not that lucky, so the slope must not be 0. The slopes, each slope. What is each slope? I don't know. It's not 0. But my best estimate is 8, because that's the estimate based on my sample. Okay, let's look at, what do we look at next? Let's look at some assumptions. We'll talk about this stuff at the bottom a little bit later. Okay, there's an assumption of linearity, just like in bivariate regression. And a quick and easy way to do that, to check that visually, is to plot the fitted values against the residuals. On the bottom we have the fitted values, the model fitted values, and on the vertical we have residuals. And we can do that really quickly. It turns out that this model object is the output of the lm command. If you just feed it to the plot command in R will plot a series of diagnostic plots of that model. And the first one, number 1, means plot the residuals. So the residuals are kind of equally spread around 0. This red line is some kind of smoother, and everything looks kind of flat. Nothing looks particularly nonlinear. If, for example, there was a cloud of points that were sort of all down here, and then sort of move up here above, and then move down below, like a big arc, then that would be a clue that there's some nonlinearity that your linear model is not capturing. But here everything's pretty flat, so it looks like it's okay. We can check the normality assumption using this weird plot called a QQ plot. And that happens to be the second plot that gets generated if we feed the model object to the plot command R. And what you want to see are these circles lining up with a straight line. And they do. There's a little bit of deviation up here on the extreme positive end, but that's really tiny. If you saw something that looked like a really extreme sigmoidal curve instead of a line, then that would be a warning sign. But that looks like it's falling along the line, which implies that the residuals are normally distributed. There is a statistical test called the Shapiro dot test, which you can apply to more quantitatively assess the normality assumption. The null hypothesis of that test is that the residuals are, in fact, normally distributed, which is what you want. So now you want the results of the test to be not significant. If the Shapiro test is significant, it means that there's a violation of normality. So you just feed the residuals of your model object to the Shapiro test, pretty simple command, and you get a W statistic. That's kind of like a T value or an F value or an R. It's just some statistic. But the more important thing is the p-value. And it's 0.6645, which is way above 0.05. So it's not significant. We don't reject the null hypothesis. And what's the null hypothesis? Is that it's normally distributed, which is good. So all is good. Yes?
Oh, just to confirm, when we're doing the Shapiro test, we always have the input, like the argument as the residuals, like every time.
Yeah, the Shapiro test is a test of whether the residuals are normally distributed. Yeah. Okay, the other assumption test is the homoscedasticity assumption. Remember what that is? It's that the variance of the residuals is constant across the range of fitted values. So we can generate that first plot again, which we saw before, and just visually inspect. Is the variance of the residuals about the same across the range? Yeah, it is. And there's not much data out here, so it looks smaller, but that's because there's less data. If we saw some kind of crazy fan shape that was small on one end and fanned out to be big on the other end, that would be a warning sign. There is a statistical test to test that more quantitatively. And in the package called CAR, there's a function called NCV test, which stands for non-constant variance test. And the null hypothesis is that the residuals do have constant variance across the range, which is what we want. So we want the null hypothesis to be true. We get a p-value, 0.11762, which is way above 0.05, so we don't reject the null. We accept the null hypothesis that the residuals have constant variance across the range of fitted values, which is good. So no violation of homoscedasticity. Okay, any questions about those assumptions so far? Yes.
The relationship between our line and the residuals, I'm a little confused about how we're going, like for the Shapiro test, how we're measuring the residual instead of the line.
Yeah, so I think that this kind of relates to an earlier question about this as well. This is kind of a quick and dirty way of assessing normality of everything in the model at once. in principle, you could imagine you might be interested in testing, well, the y variable should be normally distributed. Each x variable should be normally distributed as well. Why aren't we doing sort of one test for each of them individually? And I've seen people do that sometimes. For me, the more relevant question is really about the model residuals being normally distributed. In fact, that's if you read the statistical assumption in detail, that's actually the assumption. This is the residuals of the model are normally distributed. And so if any one of the independent variables or dependent variable was not normally distributed, that ought to show up in this test of the residuals. If this test fails, then it's true you don't know what is at fault, right? You could get an idea by looking at this plot if there was a variable in there that was extremely not normally distributed. So I don't know. I think the truth of the matter is you'll come across different approaches. In this course, the one that will be acceptable to me is testing the residuals. Yeah.
So basically, like for a bivariate regression, you would do like the usual x, y, and see like for example.
Yeah. So the question is, in bivariate regression, would you still test would you test the y variable and the x variable individually, or could you do this?
Yeah, because I guess like for the notes for last week, because it all says like y and plotting for like that one, you like also y against x.
Yeah.
So for multivariate, you would do residuals.
Yeah, I think, like I said, the truth of the matter is you'll probably see both approaches out there. It's true with the course notes from last week. I didn't do these tests on the residuals, right? I did them on each variable. In this course, either approach is okay. That's the bottom line for sort of your assignments and exams. But the truth of the matter is probably if you did stuff on the residuals, even for bivariate regression, that would be statistically acceptable. Yeah. It's a bit of an unsettling thing that I think will come up more and more the more stats courses you take. You'll see different profs who tell you different ways of doing things. Sometimes you'll get a prof who will say, my way is the only correct way. Everyone else does it wrong. If anyone ever says that, your first reaction should not be, oh, thank God, finally, I'm getting the real answer. Your first reaction should be, oh, really? Okay. You think so. Because the truth of the matter is that there are a few instances in statistics, once things get even a little bit complex, there are a few instances where there's one singular right answer universally for everything. So keep that in mind. It's a little unsettling, actually, because you kind of go into stats thinking it's kind of like algebra or math, and like, it's right or it's wrong, this is the way. But there are differing opinions. Let's go here.
To double check, does failing the test mean that we can not reject we reject the non-hypothesis?
Yeah, so the question is, if we fail this test, what does that correspond to in terms of the hypothesis? So I'll say it again, the null hypothesis of this test is that the residuals are normally distributed. And that's the assumption that we want to be true, that it is normally distributed. So that's the null hypothesis. If the test is significant, if the p-value is less than 0.05, then just like in the t-test, we would reject the null hypothesis. We would reject the null hypothesis that it's normally distributed, which is bad news. So if the p-value is less than 0.05 in these tests, it's bad news for us. We violated the assumption.
Okay, and then that would count as a fail of the test.
Yeah, that would count as a fail of the test. Yeah.
Thank you.
Yeah. We would succeed in rejecting the null hypothesis, but the null hypothesis is what we're hoping is true. Yes.
So in the plot, I believe on 23, yes. Because it's not Because it doesn't look like it's uniform. It kind of looks like it's going up like this and down like this. So would this fail?
Oh, this line here?
No, like the distribution.
Oh, I
like
see.
the
The
points.
distribution, it kind of goes up and down.
Yeah.
Yeah, a little bit. I would say, yeah, kind of. I mean, it's a little bit wider here than it is here, maybe, but it's a small. That's a small effect.
So the p-value here would be less than 0.05 for this.
No, probably much bigger. Yeah, when the p-value is small, it means the test is detecting some violation of the assumption. So what assumption is this? This is elasticity. If we had data that was like really tight here and then fanned out extremely big towards this end, and we did that non-constant variance test, that test would say, yeah, you have non-constant variance. I'm really, really certain that p is 0.00001. The chance you could have obtained non-constant variance this extreme in your sample, if in fact in the population the variance was constant, the chance you could have obtained this extreme sample is really tiny. So it must be like that in the population too. Bad news for you.
So that's normal enough.
Yeah, this is normal enough. Yeah.
So if we went and looked at our correlation matrix and we found out that there's like one rascal variable that's making everything else fail in our test,
Yeah.
would we potentially drop that variable or would we use a different statistical test?
Yeah, so the question was, if we did this plot and we saw, what did you call it, one rascal variable?
Yes.
Like, let's say we saw one variable where the distribution was extremely skewed and it was not normal, and that when we plotted the data against another variable, it was all nonlinear and it was crazy looking. What would we do? Would we just kick it out? Or would we do something fancy to correct those violations and keep it in the model? If it was me, I would kick it out. I think 99% of the time I would just kick it out. The exception is if I knew in my heart, okay, it might be a rascal of a variable, but it's a really important variable for me to include in this model, maybe for some theoretical reason or I don't know what. It's something that I know is important to the dependent variable, and oh crap, it's not linear and it's not normal, but I know it's important. So in that case, there's a whole range of things you could do. You could apply what's called a data transformation to the variable. And those are weird things, like you take the cosine of the variable, or sometimes the square root of the variable.
Like a log?
Or a logarithm. Yeah, there's a whole host of transformations you can do that will sometimes fix normality, make a skewed distribution more normal. So you can do that kind of thing, and kind of, squash the bugs and make it normal, fix the variance. The downside of that is that then you're dealing with a variable in your model that's not the actual variable, but it's some weird transformed version of it. And then when you get a slope on that thing, on that like mutant variable, the meaning of it is a bit hard to interpret now. So like let's say the variable was, I don't know, the penguin's age, and you had to take the logarithm of the age, or no, let's say the cosine. You took the cosine of the age to fix some violation, and that stayed in the model. And you got some slope. Theta 3 was the slope on the cosine of the age, and it was 10. What would that mean? It would mean that for every unit change in the cosine of the age, the mass of the penguin increases by 10. Okay, for every unit change in the cosine of the age, what? It's just hard to sort of parse out.
So it allows you
What
to
that
do the
means.
test, but then you have to deconstruct that kind
Yeah,
of.
then you have to take that and somehow relate it back to the original variable. It's possible. It's just cumbersome. Yeah. So depending on how important it is that you have that thing in, you could just kick it out. You could keep your life simple, or you could do one of these weird transformations. Yeah.
So the QQ plot and the residuals versus fitted line, both of those showing linearity?
No. So the QQ plot is really according to the normality assumption.
Oh, not.
Yeah, the QQ plot is for the normality assumption. It's a little confusing because when the normality assumption is met in the QQ plot, it means that visually this is linear. But it's not the linearity assumption. Yeah, it's a little confusing. Okay, so we check the homoscedasticity assumption using the non-constant variance test, and in this case we pass. Okay. The other thing to be cautious of in a multiple regression is this thing called collinearity. And collinearity refers to the phenomenon where some of your independent variables, some of your x variables, are really highly correlated with each other. And that can present a problem for estimating a model. Imagine you have a model with x1, x2, x3. And x2 and x3 are really tightly correlated with each other. They vary in the same way. And maybe their correlation coefficient is like 0.9. And if you plot x2 versus x3, it's like a really tight straight line of data points. So how does the model then estimate slope for x2 and for x3? x2 might predict the dependent variable in some fashion, but because x3 is so tightly related to x2, it might also do a good job in predicting the dependent variable. So how does the model decide sort of which one wins in the model? The truth of the matter is when two independent variables are really correlated, then really tiny changes in the data can flip the model from sort of one state to another and rely on x2 more or rely on x3 more. The model becomes very unstable. And so read about that in the chapter 15.9.6 that we borrow. There's ways to check for collinearity, and the numerical metric is called the variance inflation factor. And the bottom line is if you find collinearity in your data, you probably have to exclude one of the variables. So I'm not going to talk about that more here, just to point you in that direction to read about that on your own. How are we doing for time? We're at 1:30. Why don't we take a break for 5 minutes, and then we'll look a little bit more at refining a model.